Yeah, so today our topic is, as you see here, piezoelectricity. And for this, we will first go a little bit to physics. What are the properties of piezoelectric materials? They are very important materials for sensors and actuators, especially also in MEMS devices, but not only in MEMS devices. We will see the governing equation, which shows that this is a coupling via an extended constitutive equation between the mechanical quantities stress strain and the electric quantities electric field intensity and electric displacement. We will look at the finite element formulation, which then will really a finite element formulation of a coupled field partial differential equation. And we will restrict ourselves, and that we already will discuss within the governing equation, will restrict to linear constitutive equations. So we will be somewhere at the working point, and we'll then do a linearization and get a linear coupling. Yeah, and then we get after the finite element discretization, according to the mechanical field, as a second time derivative is in, it will be a coupling between an algebraic system coming from the electrostatic field and the semi-discrete Galerkin formulation, so still continuous in time. For the mechanical equation, we will do a time discretization and end up then in a discrete system of equation, which we have to solve, and where we are interested actually in all four analysis types, as already discussed: a static, a transient, a harmonic, and the eigenvalue analysis. So there are a lot of applications, and from my point of view, I just have collected some of them, as you can see here. And this is, for example, the printer heads, piezoelectric actuators, or even a servo drive is shown here. Here is a piezoelectric stack, as we call them. So you have a lot of piezoelectric layers, always in between are the electrodes, and you can use this as an active vibration damper, as it is also used in sports, here for skiing, for example. And here it will be in a case that an additional electric circuit will be attached to it, and you get then also some kind of damping in this case. A very prominent application are injection actuators, which are mostly electromagnetic ones, but you will not get that pressure and that dynamic range as you get for a piezoelectric stack. So actually what you see here, this part is a piezoelectric stack consisting of about 300 to 400 thin layers. In between are the electrodes. We will see that it's important that we have thin layers, because the electric field is the important part, and you don't want to have too high voltages to be applied. And as we know, the electric field is voltage over distance. So if you make the distance small, which means the thickness of such a layer, then you can use reasonable voltages, as you have in cars, 24 volt, for example, and you still get quite a high electric field if these thicknesses are in the micrometer range. And a very prominent application is clearly in telecommunication. So you call this surface acoustic wave filters. So with these finger electrodes, you put the electric signal on it. This signal generates here a surface wave and can be picked up by these finger electrodes. And if it doesn't match the frequency, you will not pick up here the wave, for example. And so you can really filter very efficiently and very fast even faster as with pure electronic filters here. Such a system for filtering, especially in the high frequency range, your signals as you have, for example, in the mobile phones. So, and as we see here with this electrode finger structure, we generate the wave. So this we drive here as an actuator. Here you can pick up if everything matches, so the frequencies you want to pass through. And so you see then this finger electrode with the piezoelectric substrate, the yellow one is the piezoelectric substrate, works as a sensor. And that is the nice thing, that it is a physical effect which goes both for sensors and actuators. So actually what we have is as materials, single crystals like quartz, for example, SiO2. They are from the electrical sides more or less isolators, and as we know, these isolators, this dielectric behavior we have there, we can model by individual dipoles, and that we smear over and introduce the so-called electric polarization. Single crystals, well, they are not so suited because the coupling factor, meaning how much energy you get from the electric side to the mechanical side or vice versa, is not as high, but that gets quite high if you have so-called ferroelectric ceramics. And the most prominent one is PCT. So you see it's lead zirconate titanate. Yeah, the not good, let's say, material in is lead, as we know, for the environment. But that is the material where you get the highest conversion from, let's say, when you use it as actuator, you put their electrical power and try to get out most of it as mechanical power. An important thing is that that has to be beyond the Curie temperature. So above the Curie temperature, it is not possible to get the piezoelectric effect. That is very similar to permanent magnets. We also have to be below the Curie temperature to get a permanent magnetization, or in this case, a permanent electric polarization. And then there are also polymers which have a reasonable, let's say, coupling factor, but it is not as high as, for example, in PCT. So this is very often used for sensor application. So, for example, to measure the pressure fluctuations in an ultrasound field, so in water, for example, and this is clearly mainly used here, this barium titanate as well as lead zirconate titanate, is PCT for actuator application. Okay, so let's have a look, a more closer look to such ferroelectric materials. Actually, we have a multi-scale structure, and it is very difficult clearly to bridge here the gap between the atomic level you have and then a real material, let's say a cantilever material, a cantilever, for example, in this sense. And that is, let's say, the different bridgings you have there, starting here on the atomic level, where you see we have here titanate or zirconate, we have oxygen, and we have the lead here. And if in this sense we are below the Curie temperature, you already have a polarization in this sense that the scent of the positive and negative charges on this atom level are not at the same position, and we know we can describe this as we did in electrodynamics by the so-called polarization vector here pointing in, let's say, z direction. So you have there a so-called spontaneous polarization already on the atom level beyond the Curie temperature, and within a ferroelectric domain, which I show here, for example, or I show here, that is very similar to the Weiss domains you have in a magnetic permanent magnet. You see that the polarization vector here is pointing for all the individual, call it unit cells, in the same direction. However, going to the next domain, it is totally different. And when you sum them up, then you get no resulting polarization at the initial stage. But we have already polarization on the atomic level. We call it spontaneous polarization. But according to energy minimal principle, they show all in different directions. And these boundaries you see here, you can also see here nicely. These are clearly not the straight lines here. That's just a sketch. It's here actually looking like this. And these are so-called grains, which are made of a lot of these individual domains. You can even see here a little bit the different domains. Also here, these shaded structures. But on a macroscopic scale, when you add up all these vectors, you get no resulting polarization in the initial phase. And that means we once have to polarize such a material to get a permanent electric polarization within the material. Okay, and that is this polarization process we have, which is a little bit sketched here. So we have here two electrodes. We have our, let's say, dielectric piezoelectric material. And when we apply here a strong electric field, they start to align. And that would be an idle alignment that is not possible in practical case. However, a lot of these individual domains as we have here, they will have then here a common alignment. Okay, so we see in an initial state they are randomly oriented, all our dipoles, due to energetic reasons. And if we apply electric field, then they get aligned in this sense. And if you then switch off your electric field, they will switch, some of them will switch back, but quite a lot of them will somehow remain aligned. And that will be then this permanent polarization. And we call it also you have made the material active. Yeah, that is as shown here in this diagram. Let's say we just put in here our axis. And what actually happens is the following. We start here at this point, as I have told to you, although it is a piezoelectric material, and on the small scales we have our polarizations, but summing up them all over, we get no remnant polarization. Now we apply an external electric field. So in our diagram, you see along this axis is the electric field. And please look also at the units, it's kilovolt per millimeter. So it's clear why our structures should be quite thin. Okay, now we apply here this electric field, and as you see, we increase and increase it. And on this axis, the polarization in Coulomb per square meter is put on. So when we now apply it, that is actually what happens at the beginning, nothing. Yeah? That means you need some threshold of your electric field, yeah, put on this axis, until really the first dipoles will switch towards the outer electric field. Yeah? And then you will go up like this, and the larger the electric field, the more you go towards this so-called saturation, as you can see. Yeah? So we have here really this polarization curve. Yeah, and if all of them are more or less aligned of the dipoles, then you come up to saturation. And now, when you reduce the electric field on this material, you go back, for example, as shown here, along this line, and end up here when the outer electric field is zero. So your voltage is now zero. That means you have here a thin, I should perhaps put it on. So you have here cross section, a thin disc, piezoelectric disc, and you put on here on the top electrode, on the bottom electrode, and you apply here a voltage. Yeah, and we know simply the electric field is voltage over distance, when the distance here, which is just the thickness of our piezoelectric disc. Okay, and that is important that we get, as shown here, this remnant polarization. Yeah? And clearly for materials here using in such actuators, we want to have this remnant polarization as high as possible. Now, if we go again apply a voltage, but in the opposite direction, yeah, you see, like we have in a permanent magnet, we get now a depolarization until the polarization is zero, exactly here. Yeah? And if you further increase, you see you can polarize it now exactly in the other direction. Yeah? And you again come back there to a saturation. If you reduce and reduce the applied electric field, we again come up here to a remnant polarization, now just in the opposite direction. Yeah, and if you apply again a positive voltage according to the material, then you close your hysteresis loop, as you can see. Yeah, and it is clear you have a lot of hysteresis loop there. So for example, if you go up with your polarization, just to this point, then perhaps your hysteresis loop looks like this one. Huh? And I also show here now in which direction we go through these hysteresis loops. Okay, so it is in this sense very complicated clearly to describe such materials, and to be very precise, you have to use, let's say, a correct physical model on the microscopic scale and try to bridge it on a macroscopic scale so that we can compute a full actuator. On the other hand, very often we do the following, that we have a working point, and around this working point we do a linearization. And that you see, at least here, let's say the working point is now exactly this remnant polarization. And you see, if you do a linearization here, that is the tangent at this point, it's look like this. And clearly this is the difference to the real behavior, but that already is a possibility. However, if your electric excitation is too large, so the voltages you apply, then you clearly go quite far away from such a straight line you model with a linear constitutive equation. However, we will just consider a linear constitutive equation. What is also of interest is what is shown here. So we have again here the electric field, but on this axis we have the mechanical strain. Yeah? And we will see that we can elongate our disk in this sense, as shown here, that we have it here again. When we start here, you apply here, and as you see, for quite some electric field, nothing happens, and then perhaps it really goes up like this curve here, and when you reduce it, you come back, and that what we have here is something which is coming from a measurement, because these are real measurements, so we never know where the 0 point is, and that would be the remnant strain, and that is clearly not 0 as shown here. That was just due to the measurement. This is an offset, so actually it would be here 0.15% we would have here. So you have to put this here up, and this is, as here shown, the wrong 0 line. Yeah, but that is what you really get out. That was the intention to show you. When you would do measurements, it will look in this case like this one. And as you can see, and I think this is quite interesting, is the following, that when you now again apply a voltage in the other direction, that you go like this, and you see this kind of so-called butterfly curve. Yeah, what you get out when you apply, let's say, a sine function to the applied voltage, being a quite high voltage or a very thin, yeah, and that will be the case. Our actuators, where we have the piezoelectric material, will be always quite thin, because you need kilovolts per millimeter, as you see, about 2 kilovolts per millimeter, in order to really polarize it, and you have a remnant polarization. Okay, so again here, if this is somewhere then our remnant strain, so this, and we take here this linearization, so we will have here with our material parameter describing the slope. Then for a small excitation, that would be a good model. But as you can see here, if you look at this butterfly curve, we go totally different if the excitation is quite strong. Okay, now let's have just a little bit a look to physics, where I will show you that looking at the chip's free energy, and being precise, the total change of the chip's free energy, we get all the different effects in, and the subset of our different effects between heat, mechanical, and electric fields will be then the piezoelectric constitutive equation. So the differential heat energy, as shown here, is described by the entropy. So this is S is here the entropy. T is clearly our temperature. Then the mechanical energy, being precise, the differential mechanical energy is strain contraction with the d sigma, where sigma is the strain, the stress tensor. So perhaps I should write somewhere down what this actually means. So if you have two tensors as we have here, so we have the strain tensor SIG, which we often write just as a bold S. And we know that this strain tensor is a 3x3 matrix, and we have the stress tensor sigma IG, which we also write down with the bold sigma. We can rewrite this also with, we know also with the Voigt notation. And the energy density is, as we have seen now, this S, and the contraction you write as a double point. And that you also can write as Sij sigma Ij. Yeah? Which means what you get out is S11 sigma 11 plus S12 sigma 12 plus S13 sigma 13 plus S21 sigma 21 plus S22 sigma 22. So you see clearly energy density is a scalar. It has to become a scalar. Sigma 2, 3. And our last line is 31 sigma 31 plus S32 sigma 32 plus S33 sigma 33. Okay. So you see this is then between these two tensors of second order, the contraction gives you out a scalar quantity, and it is just the individual multiplication of the entries and just sum them up, as you can see. Yeah, and so you see it is very similar, yeah, as we have for the electric energy, or to be precise, the differential electric energy, where we know, or density, where we know we take the scalar product between the dielectric field and the electric field intensity. Okay, and by doing the individual partial derivatives of our chip's free energy, we can get out, as shown here, for example, by this one, the entropy, or by this one, our strain tensor, or as shown here by this one, our electric flux tensor. And you see that you always have here some symbols as an index. That means you compute this by constant mechanical stress and electric field, yeah, or constant temperature and electric field, and so on. Yeah? So as written here, the other quantities are held constant. So if you do this, and without any details now, you see the following, that you get out very interesting constitutive equations where the derivatives are our material tensor. Now this is the variation, yeah, of the entropy. This is our strain, now here written with epsilon. If I written it here, yeah, okay. So I write it here, that's the strain. You know, in mechanical engineering, you would never use a S for the strain. You would always use the epsilon, but epsilon for us is also more or less the permittivity. So this is our problem. And therefore we have these different notations. And here this would be the dielectric displacement. And you see that in here all the different couplings, and the couplings of interest for us would be here this part, yeah, which is Hooke's law. Yeah. So you see in this sense that the strain, the stress, and that is the elasticity tensor, the compliance tensor. So it's the inverse of the elasticity tensor. Okay, and that would be Hooke's law. But you see that we also have here in the coupling, for example, when we have a piezoelectric material, the coupling to the electric field given here by, again, a tensor which we will explicitly see then. It will be easier, our notation on the other slides. And we will call this the piezoelectric material tensor. And in the last row, you see here exactly the electric permittivity given here by the partial derivatives of the dielectric displacement with respect to the electric field at constant temperature and mechanical stress. And that is our simple, what we have here, our simple dielectric constitutive equation. And in addition, we also get here the piezoelectric coupling effect because we have the mechanical stresses, and there again a tensor is coming up, which is also the piezoelectric coupling tensor in this sense given by the partial derivative of the dielectric displacement via the mechanical stress and multiplied by the mechanical stress. Okay, so without going into details to all these other couplings, you see we have then here a constitutive equation where we have here the strain, here the dielectric displacement, and they are functions of the mechanical stress and the electric field. Mechanical stress field. And what I have put in here are in this sense then our material tensors, which gives us the coupling. And actually it is an extension, that is why I write in here, perhaps, and make this in red. It's an extension by this term to Hooke's law, because this equal this is our Hooke's law. And what we have here is the extension of the dielectric constitutive equation by this term, and gives then the fully coupling between mechanical stress strain and electric field intensity E and dielectric displacement D. Okay, and that we can write down in this form here as shown. So we have here the mechanical strain written with S in our notation. And we have here, as I have shown this part here, again, Hooke's law extended by this term here. So we see that also a strain is generated due to an electric field E. And we have the extension of the classical dielectric constitutive equation. And we see that we also get the electric displacement due to mechanical stresses. Yeah, and we will use the Voigt notation, which means at the end that we can rewrite here this compliance tensor by a 6 by 6 matrix. This will be a 6 by 3 matrix, the coupling tensor. So you see this is a 3x6 matrix, and it is just a transposed. Yeah, that is what we have here in this sense. And this we clearly know is a 3x3 matrix. Yeah? And then this is nicely working with this void notation where, you know, we just have 3 normal stresses, strains, and 3 shear stresses, strains, and therefore we can write it very easily in this notation. Well, what we have just put on was the so-called deform, yeah, where the mechanical strain is expressed by the mechanical stress and electric field, and the dielectric displacement is expressed by the strain, the mechanical stress, sorry, and the electric field. That is the deform. And it is a linearization, as we have done, about a special working point. Now, the E form is that we rewrite this equation. Yeah, we can rewrite this equation to have now expression for the mechanical stress and the dielectric displacement, and that is clearly an advantage for us, because then we can directly put in this in our partial differential equations, which we will see soon. And as you perhaps already know, because we have discussed the mechanical PDE and the electrostatic PDE. So this here, as we see now, is just a reformulation of the D form, gives us the E form, where we can express the mechanical stress as a part where we have the mechanical strain and the electric field, and a part again for the dielectric displacement as a function of the mechanical strain and the electric field E. And if you do this by hand, so this is, since we here just are looking at algebraic vectors and matrices, you will see simply this relation between the compliance tensor and the stiffness tensor. See, we have the relation between the coupling tensor, piezoelectric coupling tensor in E form, and the piezoelectric coupling tensor in T form. And we have here the dielectric, the permittivities at constant strain. So that exponent means at constant strain. And this means at constant stress. Yeah? Okay. And so you have also this relation as we have here in this E form, how to compute this permittivity at constant strain out of the permittivity at constant stress as we have in the D form, the coupling, piezoelectric coupling tensor D, and the mechanical stiffness tensor. And that also means here, it's important, yeah, that also means when you measure these entries of this material tensor, you have to measure it at constant E field. Okay, so in this sense, then we can look really at the entries of all our material tensors. More or less for most piezoelectric materials, we have there a transversal isotropic material, which means that it is just different in the thickness direction where it is polarized. Yeah. So if I go back, I had somewhere my disk. Yeah, okay, it's not as nice. So let's make here a new sketch. Okay, so let's say this is your piezoelectric plate. And on the top and on the bottom, you have there your electrodes. Yeah? So you have here an electrode. And we put in here now our coordinate system, which is simply X, Y, Z. Yeah. So you see, when you apply a voltage, you would have here polarization in Z direction, and that is mainly, as you will find, these material tensors, that it is assumed that they are polarized in thickness direction. And then you get this anisotropy just in the thickness direction, and you are isotropic in the XY plane and get different in the Z plane, and that means transversal isotropic. And that also means when you have in your finite element model your piezoelectric actuator somehow aligned, that you have to transform the matrices or these material tensors in this direction in order to do correct computations. So what we see here, this is our stiffness tensor as we know it here. And if you look down, then you will see that it is 5 entries which are different from each other. We see here our E piezoelectric coupling tensor, which you see have 3 entries which are different. And we have the permittivity tensor here very nicely seen, this transversal isotropy, because you see in the XY plane the same permittivity, and this is different in the thickness direction, as you can see. So it is 2. So we can summarize, we have here 2, we have here 3, and we have here 5. So which means we have to measure 10 parameters. 10 material parameters. Yeah? So this is a quite complicated task and not easy to be done in a lab. So if I go back, then we see also that we have to fulfill something in our measurements. So for example, if you need the permittivity here at constant stress, you have to have a measurement setup where, let's say, this is the sample where we have no stress here, because we have to measure then here our dielectric permittivities at constant stress. And the easiest way clearly is to have the sample free hanging so that the stress is more or less 0. Constant stress also is 0 stress. Yeah? It's not necessary to have 0 stress, but constant stress, and the easiest way is to have a setup like hanging the sample, and then you get this 0 stress. Constant strain is almost impossible. How can you guarantee that you have no constant strain? Means that you have here in this sense a fixing where the strain is constant. That's more or less impossible. That is why you always in measurements you have experimental setup of your sample that you more or less can guarantee constant stress being zero stress because your sample is not fixed at any point. Yeah, so possibilities, let's hang it down. And in addition, we also have to be careful. We also have to evaluate, as you can see here, for example, our classical Hooke's law, where we try to get here the entries of the mechanical stiffness tensor at constant electric field. How can we have a constant electric field? Because we have this full coupling here, or if you look here or here, so any change in a strain will also give a change in the electric field. Somebody has an idea, how can you guarantee this? So I've told you how you do it for the permittivity. Try to have no fixing of your sample to guarantee more or less zero stress. The idea to guarantee somehow a zero electric field. Okay, so I give you the answer, and the answer is simple. If you want to clearly know it, so these are the electrodes. Yeah. So let's say
you can short circuit them.
Yes, very good. And that is really the case you have to do. Yeah, you short circuit it. Exactly. So when you do this, you have to short circuit it. You guarantee zero electric field, and that makes sense, as you can see here. Yeah? Then this is zero, and we have more or less the classical Hooke's law, and you can use the classical setup as you do for classical mechanical materials. Okay, so you see it is a lot of work in this sense to get all these material parameters. We have to measure them. You cannot directly measure them, so you measure something like mechanical elongation or the electric impedance, and then try to solve this more or less inverse problem to come up to all these different material parameters as we have seen. But you see, we need it in order to be able to do numerical computation. And this is the case for linear constitutive equation. To get the idea how large the different entries are, so we have here two different PCT materials, the PCT material 5A and 5H. You see we have here the mechanical entries of the stiffness tensor. We have here the coupling, the piezoelectric coupling of the piezoelectric coupling tensor, the entries, and here our two permittivities. And you see that they are quite different. Yeah? This is gigapascal, so actually that is to be multiplied with 10 to the power of 9. And this here is just a relative permittivity. Yeah? So they are actually very small because you know our epsilon 0, the permittivity of vacuum is 8.854, something like this, 10 to the power of minus 12. Yeah? So in this sense, quite different values for all our entries in the different material tensors. Okay, so we see, or let's say, hopefully we have given somewhere from a material database all these entries. Be very careful when you do simulations in practice. Mostly what you get from the manufacturers is not correct. So don't believe the values from the manufacturers. In this case, it would be good to have the possibility to measure these material parameter entries by your own. So, as I have told you, we have a mechanical system where we have the balance of momentum. So we have here the inertia force, we have here our P operator or differential P operator operating on the mechanical stress and any volume forces. And we clearly also know the nice relation between strain and mechanical displacement, which tells us in this case how we get out of the mechanical displacement then the strain. And we already also have our extended law here between these, which is not only Hooke's law, which also has to be extended to the electric field, yeah, as we just have seen. On the other hand, we just have to model electrostatics. So it is really that the curl, as we know, of the electric field is zero, since we assume to have there are no magnetic or time-changing magnetic fields, so we can again express the electric field by minus the gradient of the scalar potential. And since our material itself, the piezoelectric material itself, is an isolator, we can model it by the divergence of the dielectric displacement being zero, because we have no free electric charges. Okay, so we have now here our equations, and we have nicely here our linear constitutive relationship, where we now can put into our equation here this expression for the mechanical stress as a function of the strain and electric field E. And we know for the electric field E, we can substitute the gradient, or being precise, minus the gradient of the scalar potential. And for S, we can here substitute BU. So you see that this here is put in here, and what we have here we put in here. And in addition, we explore the strain displacement relation and the electric field scalar potential relation. And we see that we get now fully coupled partial differential equations, for which we are now looking for the weak formulation. So in this sense, we have now a model, and most importantly, also we directly see that we have here, when we apply any voltage to our electrodes of the piezoelectric actuator, for example, we immediately have our electric field, and that makes this actuator as fast. The only term where we have restrictions is our inertia term. Yeah, clearly, the more mass you have, the larger your time constant. Okay, so what we do here now is that we still use, when we do in this sense, the weak formulation, we still use here this partial differential equation written here for the second time derivative of the mechanical displacement. Perhaps I should also write it in this sense. Yeah, within the finite element method, you like to write the time derivative as a double point, and we use here this equation. Yeah, so, and then after we have done the integration by parts, meaning we have applied the Gauss theorem, we will do the substitution as just described. Okay, so as written here, for each PDE, we introduce a test function. So we have here the test function U prime, a vectorial test function for the mechanical PDE, and a scalar test function for the electric BD. And as you can see here, what we have here is our inertia term, here the term according to the stresses, and here a term according to any given volume forces. And this is just our equation as we have Gauss law for an isolator where we have no free electric charges. Now, applying the integration by parts, or as in multiple dimension, we call it the Divergence Theorem, we get the following. So on this term here, we get now our differential operator operating on U prime, as shown here. And in addition, we clearly would have a surface integral, but we neglect it because we assume that the stress in normal direction on the surface is 0. And the same is assumed here. We do here also apply the divergence theorem. So we get here just this term because we assume homogeneous Neumann boundary condition as written here. So both for the stress as well as for the dielectric displacement D. Yeah, and now we can use our relations. We use our extended material law and can substitute now in this equation our stress, sigma, and dielectric displacement via this constitutive equation. And in addition, then also we use the relations shown here between the strain and the mechanical displacement via the differential operator B and the relation between the electric field, which is in here, and the scalar potential. So if we do this, we come to our final weak form as shown here. So we have our standard term as we have in classical mechanics due to the inertia. Here there is some additional which should not be here. Then we have our classical term as we have it in mechanics. And in addition, and this is now the important thing, we have here the coupling term coming from the electric field expressed here via the scalar potential. So we see how the electric field couples into the weak form of the mechanical equation. And in addition, if we look here, we would have here the standard weak form for the electric field, and we see how the mechanical field couples in via the mechanical displacement, where we have the differential operator operating on the displacement, and the coupling, or simply called piezoelectric material tensor E, yeah, as we also have in this term here. Okay, so we see that we get a fully coupled system of equations. We don't have to consider special properties. We can use our standard nodal finite elements where the unknowns are at the nodes of our finite elements. We have here a weak formulation as a function of the mechanical displacement and the scalar electric potential. We use the classical ansatz with the basis function and apply it to our weak formulation as just shown here, yeah? And substitute this and end up in the semi-discrete system of ordinary differential equations because we are still continuous here in time. Yeah? So we just have extended here the mass matrix, but you see that here are just zero matrices because the time derivative of phi is not showing up. The second order time derivative or first order time derivative is not showing up in our equation, but in order to have it here as the same size for the overall matrices, we also put in zero matrices. We can also model here any damping, pure mechanical damping, And then you see all the coupling comes up here in the stiffness matrix, where we have here the stiffness matrix of the mechanical system, the stiffness matrix of our electric system, and the couplings. And in order to get in symmetry in this extended stiffness matrix, we have multiplied here with -1. That is why a minus is here. Yeah, let's look back. You see, you have once here the coupling with a plus, once here the coupling with a minus. And if you have a close look, you see it is the P operator on the test function of the mechanical test function transposed, and here the gradient of phi. And when you transpose this, the total term, then you have here the gradient of phi, which is now the test function, and you have here the P operator operating on U. But you know, since we use the same basis function for approximating the displacement and the scalar potential, the discrete matrices will be just transposed to each other, as just shown here. Yeah? So I can also explicitly write this K U phi is equal to K phi U transposed. And that is why we multiply here this equation with -1, and then we have a minus for our classical term we have in electrostatics, and that gives us this minus we have here. Okay, but then it's good that we remain symmetry, and we don't have to store the whole matrices, we just have to store the upper part and the diagonal part of each matrix, and so can reduce the memory needed to store the matrices. Yeah, here just explicitly written down here, this coupling matrix is we have here, and again what you see here is this here constriction, as we call it, in order to get here the correct evaluation. Okay, so you see we have now a model approach for our piezoelectric sensors and actuators. We have the finite element formulation of it. Yeah, here we know that we will also have to do a time discretization, but for the time discretization we will do just what we have done for the classical mechanical system. We will apply a Newmark method in order to get then at the end an algebraic system of equation for mechanical displacement unknowns and scalar electric potential unknowns. Clearly our assumption was small strains, linear piezoelectricity, so we have linearized it. We don't consider here the hysteretic behavior. We assume a perfect homogeneous polarization clearly, and we do not model actually the electrodes in this sense. So for us they are perfect, and since they are so thin in practice, also in most cases you don't model it really as a thickness structure, the electrodes, you make it infinite thin, so which is just written down here. Yeah, and as I have told you, all four analysis types are of interest. So very often, yeah, we have just a very the actuation is in a sense that it is not time dependent, so we just do a static analysis. If the actuation is in a sense that we are interested in a steady state solution, so you excite it with a sine or cosine function, you want to have the steady state solution, you do a harmonic analysis. If you are interested in the transient, you have any excitation function, then you have to do the transient analysis. Yeah, and we are also clearly interested in the eigenvalue analysis, especially in order to see that at which eigenfrequencies we really get a coupling between the electric field and the mechanical field. Yeah? When you do eigenvalue analysis, you will see that you will also find a lot of eigenvalues which are pure mechanical eigenvalues, and just some parts, some eigenvalues are really coupling eigenvalues, and they are clearly of interest for us, especially when you design a sensor. Perhaps you want to do the sensor or even also an actuator and do it at the resonance frequency, then you want to have this resonance frequency to be a coupled resonance frequency and not a pure mechanical resonance frequency. Yeah, that would make no sense. Okay, so concerning boundary conditions, well, the boundary conditions are somehow clear. We have to the classical mechanical boundary conditions we already have discussed that we fixed. Let's say you have an actuator like a cantilever actuator, and it is fixed on one side and can move freely on the other side. So you put there zero displacement, so homogeneous theoretically boundary condition for the mechanical degrees of freedom at the fixing. The electrodes, as we have already discussed, are modeled in the sense that we have infinite conductivity of the electrode, so we don't assume any resistance there. Sometimes we have to solve our finite element equations together with a network equation. So in order to have also the, for example, the power electronics in how you feed and load electrically your actuator. And one of the important values then in a post-processing step is the electric impedance, which can be simply computed, as we know, voltage over current. Now here just written down the current, as we know, is the total change in time of the charges, and that is clearly computed out here by the dielectric displacement D. And please remember that D is a function of both mechanical displacement and scalar electric potential. Yeah, so we have to take this into account and use here, then when we express D, our extended constitutive equation. Or if you write it down in the frequency domain, we know the time derivative is just a scaling with j omega, j being the complex unit, and so we can evaluate as written here along the surface of your electrode, and you get then the total current as a function of frequency. We have applied, for example, there inhomogeneous theoretically boundary conditions for the potentials, which means you know the voltage, we compute out the current, and then have the impedance as a function of the frequency, for example. Yeah, and that is just coming to end at this lecture unit. As I have told you, often it is you have a special setup and your actuator or your sensor is not as aligned to the coordinate axis there. As you have your material parameters, where we assume that we have the polarization in thickness direction, then you have to do a rotation of your material tensors as shown here in order to do a correct computation. That will be also discussed in detail then in the exercises where you do additional commands in your XML file. Okay, so you see that we can model piezoelectric materials quite nicely from what we already know, the electrostatic field and the mechanical field. And we use an extended constitutive equation which relates the electrical and the mechanical physical quantities, and come up then to our, at the end, weak formulation or intermediate step, and at the algebraic system of equation, where we also have to discretize in time, where we use the classical Newmark method. Okay, are there any questions so far to this model approach for piezoelectric sensors or actuators? Yeah, if this is not the case, then thank you for being online, and we see next week, where we will first have some additional modeling approach to see what we also do in latest research. Where we will also include hysteresis, or where we will even be possible to model the polarization process. And afterwards we come to our last chapter, which will be the acoustic wave equation and the coupling to mechanics, so that you are also able to model any vibroacoustic systems like a loudspeaker.